So welcome to From Whiteboard to Mainnet. This is a podcast that is a collaboration between Columbia University's Center for Digital Finance and Technologies and the Ethereum Foundation's Academic Secretariat. I'm Fahad, alongside Shyam. We will be your co-hosts. And we have, and I should say before we sort of get into things, that sort of the name of the podcast very much speaks to what we're trying to do here, right? So this is a podcast that is supposed to basically take academic research that is practically relevant and practically important and expose it to industry, researchers and engineers. And so we're very excited today to have, in our inaugural episode, three awesome guests. We have Ciamac Moallemi from Columbia University, and Maria and Davide from the Ethereum Foundation. And the topic that we're going to be digging into today is optimal design of rollups. And this is actually going to be from the perspective of sort of more, I would say, finance and operations. So the hope is that it's actually going to be very useful and interesting, even for instance, computer scientists who've been spending a lot of time looking into these things, but from a different perspective. And of course, this is also supposed to be, very, hopefully very insightful and interesting for people from the more economics, finance, and operations side. But so, let's not waste too much time here, and let's sort of dig into this. Before I'm going to do a little bit of level setting before we get into it, just to make sure everybody's on the same page. And so very quickly then, maybe Ciamac, if you could start us off. What is a rollup? What's the purpose of having these in the first place? And what does it really have to do with the layer one Ethereum?
Sure. Happy to explain that. And thanks again for the invitation to be here today, Fahad. So basically, the core idea of rollup is a scaling strategy for Ethereum. The idea is that in the absence of roll ones, the Ethereum L1 by itself is bottlenecked by the fact that it's designed to be able to be validated on machines with limited computational limits, and it's also fundamentally sequential. A rollup, the idea of a layer 2 rollup unlocks two things. On the one hand, you can have one of the main resource consumptions of transactions, which is a computation. Instead of doing that on the Ethereum L1, we can do that elsewhere, right? So we move the computation off chain, and that allows scaling the computation. And simultaneously, by having more than one rollup, we can have these computations going on in different parallel streams. So those are the core ideas of the rollup. The way the rollups relate, which are layer 2s, relate back to the layer 1, is they want to inherit some of the economic security of the layer 1. So if you have users who trust Ethereum and trust the system with a large number of diverse validators and significant economic stake and so on, the idea of building a layer 2 on a layer 1 rather than creating a new layer 2 is you can inherit some of those properties on the rollup chain as well.
Okay, all right, and so maybe thinking a bit sort of more in the sort of getting into some of the work that you and Davide have been doing. Another sort of a bit of level setting question I want to go into here is that since you're thinking about the sort of optimization of the rollup operator, the sequencer, could you talk a little bit about sort of the life cycle of a transaction when you're doing it on a rollup?
Sure.
Maybe.
So the starting point would be that the user submits the transaction. On rollups, there's typically not a mempool or anything like that. Rather, the most common design is that there is a centralized sequencer. So you submit your transaction to the centralized sequencer, and the first thing that sequencer does with the transaction is within the universe of that rollup decides how to order that transaction versus other transactions it may receive. So different rollups do different things. Some are first come, some first serve, some are priority ordering, right? Once it establishes the order of that transaction with respect to other transactions, the next thing that the rollup does is it executes the transaction and sees what the state change was, and so on. And there may be some decisions as well. For example, some rollups offer revert protection, where if your transaction is going to fail, it's not included. So far, the main things that the rollup has to do is to order the transactions and then to execute them. Typically at this stage, the user gets some kind of local confirmation that their transaction has been run, a so-called kind of soft finality. So the sequencer may report, hey, I saw this. But then what's going to happen next is those groups of transactions are going to be batched together, and then they're going to be posted to the L1. Right, and that's the core of the sort of the economic guarantees that rollups can give, is that things are sort of posted to the L1, and then downstream can be verified by anyone else. And this is where sort of the heart of part of the problems we've been analyzing are, which is how to do that. Right, how to batch transactions and when to post them on the L1, being kind of cognizant of for example, the cost of posting on an L1 may vary over time. Maybe there's different ways to post the data to the L1. You can post call data, or you can post these objects called blobs, and so on and so forth. So the transactions then hit the L1, and then finally maybe the next step is once there is sort of finality on the transactions that have been posted to the L1, then you can get the economic guarantees. I neglected to mention one other thing that the sequencer or operator is responsible for, and that is setting fees on the L2. So just like on an L1, where you may have base fees, priority fees, whatever. On an L2, you may have similar kinds of fees. So the core kind of economic issues we're sort of thinking about are number one, how should the sequencer think about setting the fees, and number two, how does that interrelate with the idea of how the sequencer and when the sequencer chooses to post transactions to the L1.
All right, cool. So that was a lot of context there, and I want to make sure that it's properly digested and unpacked. And so actually, you mentioned things like you used the word blobs in there somewhere. And of course, I think for people in the Ethereum community, it's now very familiar. But maybe we can take a step back here right now for a moment, and I don't know, Maria, could you provide a little bit of context on sort of the evolution of, let's call it, the behavior of these layer twos, particularly because we didn't always have blobs, right? And so what did layer twos do 3 years ago, and when did they start what is a blob, right? And when did they start actually taking advantage of that, and maybe even thinking forward, because there's more activity around blobs even related to the last upgrade, Pectra, and in the future. So yeah, please provide some context.
So before March 2024, which is when these new blob carrying transactions were introduced in the Ethereum protocol, before that time, what rollups did was they used these space in the transaction, let's say, called call data. So the initial design for that was every time you want to run some contract and you need to add inputs to that contract, so you need to specify some additional data or parameters, you can use this open space in the transaction to carry that data. But this is fairly expensive. So first, you sort of have to make this data available for the entire network when the validators are executing the transactions and making sure they are correct. And second, this data would continue to live on. And so it would kind of have a weight on the whole network, because you are requiring this data to be stored indefinitely. So this was quite expensive. After March 2024, this new blob carrying transaction was introduced. And so now there's this new type of transaction that has actual space for, and it was designed for rollup data. And the key difference is that now this data doesn't live, doesn't need to be stored indefinitely. So it can be dropped off after a few weeks. And so this should be much more cheaper than the call data. And so these actually led to sort of a revolution and changed significantly the fees that users were paying on the L2, because now rollups could post their data much cheaply, and so they could charge cheaper fees to their own users. And maybe we can go on this discussion more at the end, but there are planned upgrades on this that will even make these block carrying transactions much lighter and more efficient for the whole network, which should unlock further scaling.
All right, so maybe let me just sort of recap a bit here. So on the one hand, it sounds like when a rollup operator is operating, there are kind of two important decisions, which I think the work that Davide and Ciamac have talks about, and we're going to get into that, which is one decision is kind of when do they post to the layer one, and another one is more of a pricing decision, right? Having to do with how the fees are set. Because I think one thing that Maria, you were talking about is that like when we think about when you think about gas fees traditionally, if you're thinking about like one number, you're probably not thinking about the number that we're talking about here, because the number we're talking about here is associated with posting blobs and not posting sort of regular execution data. Although, of course, even in the context of regular execution data, base fee, priority fee, there's some complexity, and we'll get into that because Ciamac and Davide's work does get into that. But before we get specifically into the most recent paper that Ciamac and Davide have, Davide, you've been doing work even earlier on related stuff, and so I wonder whether you can provide any context on sort of the earlier work, sort of as a precursor before we get into this discussion.
Yeah, so I've been interested in pricing problems for a long time. And actually, this is also one of the way I got closer to like the Ethereum core development. It's by looking at some improvements to the layer one, the EIP 1559 fee mechanism.
Quickly, can you remind us what EIP 1559 did to the transaction mechanism?
At this point, like everyone assumes that this is common knowledge, but maybe it is not. This is like a much talked about change. Is one of the most, I would say, one of the biggest, most impactful changes to the Ethereum layer one protocol after the merge, after the switch to proof of stake. I feel that this ranks in the top 2 or 3 of changes. So basically, what happened with this is there were like a few issues on how the Ethereum transactions were priced historically since the beginning of Ethereum, and this was a model kind of similar to Bitcoin, where like if you want a transaction to be included, you need to essentially like participate in essentially what it is first price auction by like bidding up the transaction fee so that the miner is going to pick up your transaction. But there were like 2 key issues. Like one was around UX. It's like users don't have a good way to estimate how much they should bid, right? And then like a time of congestion, like that becomes quite challenging. And so like the idea was, okay, can we come up with a mechanism that is kind of like simpler but still has good properties, right? And I think there was a breakthrough. Probably the academic community can relate to that. I think around like 2018-19, Vitalik has these original ideas on how to do this. He had like kind of an early draft of a paper, but then he went to the EC conference, and I don't know if he spoke to Tim or like to some other like economists at that conference, and then like actually like the current form of 1559 was crystallized. So what it essentially does, basically there is like a base fee, which is essentially a dynamic price that is fluctuating based on like demand supply imbalance, and then there is a priority fee, which is a tip. And the core property is that the base fee gets burned, and this is like for economic reason, because essentially the base fee cannot go to the miner or now the proposer, because otherwise this is not setting the right fee is not incentive compatible for them. So some rollups actually, what they do is they put these fees into the treasury. So I believe that this is what Arbitrum does. Like basically this base fee goes into a smart contract, and then the Arbitrum DAO, basically it's a way to like collect revenue and then distribute it for public goods in the ecosystem. But for the layer one, essentially there is this principle of governance minimization. So there is like a huge amount of fees that come in this way, and like the idea was that we don't want this to be a centralizing force and to have like some heavy operations to distribute these fees to whomever like may need them in the ecosystem. So the easiest way is that you burn them, and that way basically the value gets redistributed to the entire population of ETH holders uniformly via inflation of the ETH token.
Right. Okay. So just to kind of maybe summarize a bit there, your point is initially it was a very simple mechanism, which is what Bitcoin uses, right? Which is a first price auction. But now what we have is we have a base fee and a priority fee. You essentially have to pay the base fee to get on a particular block. As you said, it's dynamic across blocks. It's like a reservation fee to get on the block, but you can still pay an incremental fee because you might care about things like priority within a block, right? So I've heard of this like as a sort of thinking of it conceptually as a segmentation. The priority fee essentially captures within block priority, and the base fee captures across block. But an important point of what you said there is the sort of dynamic nature of it across blocks, and I think that's going to come into play a little bit here with your work with Ciamac. But let's not bury the lead. You know, Ciamac, you provide a lot of content up front, and one of the things you were talking about was the results in this most recent paper, and particularly the first part of it about sort of the timing of the posting and the optimal strategy for posting, right? So if I'm a sequencer on a layer 2, when do I post these transactions to layer 1? That's an optimization problem that needs to be solved, and it's good we have the experts here in optimization, yourself and Davide. So Ciamac, could you just tell us, what do you find is the optimal strategy for posting, and could you also give us a flavor of why the intuition behind it?
Sure. So the optimal the flavor of optimal strategy we're trying to consider is one that optimizes a cost model that we have. And just to sort of set up what the goal is, the cost consists of two components. One is a if you want to say a real physical cost, which is that you have to pay the layer 1. Be it if you use call data, or be it if you use blobs, there's a price of each of those on the layer 1, and you have to pay it. So that suggests the intuition that all things being equal, you want to post when those prices are low. Kind of the second component is the waiting cost, right? So this is a little bit more of a conceptual device. There's no, if you delay posting a transaction, there's no specific charge. Sorry, I'm posting an L2 blob. There's no specific charge that you incur. But all things being equal, systems operate better if the blobs are posted in a timely fashion and others can verify them. And also, so our cost model also has a delay component, which motivates, all things being equal, posting things early rather than later. So
can I just interject briefly on that point about, so you're saying, look, there is an actual cost when you post, and the fees are dynamic, so you want those fees to be low, all things equal, but there's a countervailing force in your analysis that you're saying doesn't map to, let's say, an out-of-pocket cost. It's a waiting cost, but and you described and sort of I'm wondering, sort of coming at it more as an economist, is there is there demand effects is kind of what I'm wondering for delay. Like if a sequencer chooses to wait a long amount of time to post, does that have downstream consequences on users such that they would be less likely to use the layer 2? Because I think in some sense you weren't giving yourself enough credit about sort of thinking about this cost. And it seems to me there has to be some kind of implication to the users. Like if a rollup just decides they don't want to post for, I don't know, 5 days, isn't that a problem?
Yeah, so 100%. So at some point, you start to lose the economic guarantees. Now, maybe Davide can comment more on the practical angle. I don't think, if a blob is posted now versus a minute from now versus 5 minutes from now, I don't think that really makes a difference. But probably if you start to getting into, days, and certainly more than a week, I think that would create problems. But I don't know if you want to weigh in on this, Davide.
Yeah, sure. I think it's safe to assume that there is an effect on demand, but it's definitely hard to measure. Also because you can have shortcuts in the sense that okay, if you are willing to kind of use some third-party bridge service and trust this bridge, then you can actually accomplish you can move your assets in a much shorter time that the actual 7 days window that it takes from when everything is posted, including the data, to when the transaction is finalized. But I feel that it's kind of hard to measure, but it's important to assume, because if someone starts withholding data, then maybe this would also become an issue of public discussion, and it can hurt even the reputation of that chain. So there is definitely going to be an effect, which we try to capture with this cost. The cost is mainly based on our discussion with L2s and how they're thinking about it, right? For example, I remember that in some early discussions with Arbitrum, they were saying that on average they try to post within 10 minutes delay, and they feel very uncomfortable even if it goes close to an hour.
Yeah, and I would also add there's another factor for ZK rollups. So ZK rollups are rollups that instead of being optimistic, they actually generate proofs that say, okay, this state change is valid, and so the draw periods are also shorter. But essentially for them, there's also this constraint where if your batch has too many transactions, it's actually unfeasible to prove. To generate a proof, it gets too complicated. And so for them, there's also this additional constraint that they cannot wait too much, because then their batch has too much circuit complexity for their prover systems to actually handle. And so there's also this additional constraint, which is not a linear thing, it's more like a threshold thing, but yeah, there's also that factor.
Yeah, I guess we also have a significant, audience from the academic side who are sort of crypto curious, but might not really understand the intricacies of the protocol. So if you were to sort of use a mental model, which is pretty similar to the physical world, given all these complexities, what is the closest that you could think of possibly that would, be a good parallel to, the whole problem of transaction posting of layer twos?
I don't know, maybe some kind of shipping problem. Maybe I'm making T-shirts in New York, and Davide is in San Francisco, and he's selling my T-shirts. And so I'm producing T-shirts at a constant rate, and I have to decide how often to ship them to him. That would be sort of posting on the L1. And maybe the considerations are how much is the shipper charging today? What is the volume of the T-shirts, and how many fit in a box that I can ship, and so on and so forth. So I think it has. That has strong analogies to a problem like that, or maybe inventory type problems. Let's say you're a retailer and you're stocking T-shirts, and you need to figure out how many to order, and you want to maybe order them on days when shipping costs less, and you want to order them in batches to sort of amortize fixed costs and stuff like that. I think there's a lot of analogy to those types of problems, which are quite commonly studied problems in operations research. I would like to circle back to kind of some of the considerations. So we sort of went on a tangent to sort of talk about the different costs and considerations. What is the optimal algorithm we come up with? Well, we come up with an algorithm that has two components, right? So one is you have to monitor the L1 prices, right? And it's sort of obvious that if it's cheap to post on an L1, maybe you're going to post more often, versus if it's expensive, maybe you're going to wait with the hope that maybe later prices will be less. So that's one component. But the second component has to do with how you batch transactions. Excuse me. As Maria already alluded to, if I want to pack, like, let's say, I don't know, 5 transactions in and post them, I have to sort of think about what the cost would be on an L1, and in actuality it's complicated, right? There may be some ZK proving costs which are nonlinear. Also, if for example, if you're posting in blobs, that cost itself is nonlinear, because a blob is a certain amount of space. I forget what it is. It's let's just say like a megabyte, right? And you get charged for that full megabyte, whether you use 1 byte or whether you use, like, 999 kilobytes, right? So there's a lot of complexity there. We sort of, as a modeling device, simplified it into 2 components, right? One component is that there's a fixed cost, right? So anytime you want to do anything, whether you're posting kind of 1 transaction or 100, maybe there's like some base gas that you have to pay, maybe that captures some of the discreteness of blobs, and so on and so forth. But as soon as you're posting at least 1 transaction, there's a fixed cost. And then we add a linear cost, which is the more transactions you post, on top of the fixed cost, you have a linear cost that sort of builds up. And the idea here is to capture the fact that, although it's not precisely 100% linear, at some level, if you start posting more and more data, you're going to consume more space on the layer 1 in some sense, and it's going to sort of charge more. So, putting that together with having a model for the dynamics of the gas on the layer 1, you get a policy which does 2 things. First of all, as I mentioned before, it tracks the gas price on the layer 1. And as a function of every gas price on the layer 1, there's some minimum quantity of transactions on the layer 2. Whereas once I have more than that quantity, I post it all. Right, and the general idea is that when gas prices are low, that minimum quantity lowers, right? You're more quick to sort of publish stuff. As gas prices go high, that minimum quantity increases, because maybe you want to be a little bit more conservative, and you want to wait and potentially post later when the gas prices are low. But the key idea is, because there is a fixed cost that you have to pay whether you post 1 transaction or 100, that you want to wait for some minimum number of transactions in order to kind of amortize that cost across all of those transactions.
I see. So, okay, I'm trying to think forward now about, so, I suppose ideally we would love to have lots of rollups to avoid things like market power dynamics. Now that in fairness, Base is responsible, I think, for like 40% of the throughput or 50% or something like that. And obviously there are a bunch of other really big ones like Arbitrum. But if we think about, for instance, a lot of rollups using the same policy, and we imagine something like positive correlation of transaction demand across the layers, because people are just doing a lot of stuff right now, because Ether prices or whatever doing something. Is there any how do you think about your result in that context, I guess, is what I'm thinking? Because on the one hand, I think we didn't explicitly say it, but right, there is a maximum amount of blobs that can be posted to a particular block. I think post Spectra it's 9, or Davide, is that wrong? Or
yeah, it's 9 post Spectra, which was in May.
Right.
But it's going up to close to 100 in
of course,
December. Yeah. So yeah.
So if I could just
for the purpose of modeling, there is no blob limit. No, please finish. I think this is a good point, but I think I want to make some remarks on this. I think it's
sure. So there's one piece which is a hard constraint, but the as an economist, I like to think about it as like prices and quantities are 2 sides of the same coin, which is to say the quantity is let's say max of 9, and in the future maybe 100 or whatever it is. But even, for instance, if you don't hit full capacity, you might start to see price effects. And I think, Davide, you've looked at some of this in your earlier work too. But I guess I'm just wondering, in a world with multiple active rollups, is it clear, or how do you think about the policy that you're proposing in this context? Is there any concern that you might see periods of time where they all try to post and then they're just, for instance, either the block is full and they're not able to, or you see big spikes to prices to post blobs?
Yeah, I see. So when you say like price effects, even if you don't hit capacity, like what do you mean? Like,
so is there a priority fee to post blobs?
Oh, yeah. Blob transactions have a priority fee, which is
Right.
like the normal, like the regular gas, essentially. Yeah.
Right. So that's the price variable that could respond, right?
Yeah, correct. But I think this is not going to change the policy in our framework, because essentially, like that posting cost is accounted for.
So maybe it's like you have to properly internalize the effects of potentially everybody doing this or something like that, right? Like it's sort of like the dynamics for the pricing is a little bit, let's say, endogenous, if I use economic speak, as opposed to
I guess maybe like if I have to think on my feet of like what are the most important effects if there is like thousands of rollups that are posting. Yeah, the number one is what I was talking about, like the blob limit. That, okay, if you hit the blob limit, we didn't really consider that case in our analysis. I also think that if that happens, it's kind of a bad state for Ethereum, because essentially you don't have enough supply of blobs for like all these transactions. I think essentially like posting cost will start growing too high, and then it's as if we are overtaxing these L2s, and then I think there is a problem there that they could move to like alternative DA layers that are cheaper and things like that. So I feel that like for the time being, that's why I was kind of like half like making this remark about this point, that we don't want to be in that case, right? The Ethereum roadmap, one of the three pillars is scaling blobs, and precisely the reason why is because we want to be in a case where there is a slack of data. And actually, maybe a brief point on that. So in Fusaka, which is the next fork, there is going to be like this big upgrade called PeerDAS, which will push to like around 50 target and kind of closer to 100 blob limit. And then after that, there is some other changes which are going to be deployed in between forks, where like as we make improvements on the networking, and there is also some improvements on blobs mempool in the layer one, we can grow several order of magnitude. So my view is that for the next maybe 5 years, I think we shouldn't worry about this, and hopefully like within this time we find some solutions on the layer one where we don't need to worry about it. The other point could be that, okay, if there is so many layer twos, then maybe if these layer twos are heterogeneous, there is like maybe some bigger L2s that can efficiently pack the blobs, and then some smaller ones that actually have like some efficiency factor which is much lower, and then like the cost could be like overburdening them. I think here the Ciamac analogy of the container is quite interesting, right? Like if you think of a blob of a container that you need to pay for the full container, I think here, like if this happens, there is kind of other solutions that could pop up, which is kind of this blob sharing idea. Like I had actually we did a brief analysis on this, like in a previous paper, and actually back when there was as soon as blobs became real, people did not realize that for quite a long time we would have oversupply of blobs. So people were starting to get worried exactly about this problem, and a few people built prototypes of how to do blob sharing between different rollups. Then those prototypes were not used because there was no need for it. But I feel that if that happens, those new engineering solution will pop up. I feel that the analysis still hold, but maybe in those cases, it will become more relevant to look at these sharing schemes. Yeah, so these are the two things I can see.
Absolutely. So, so basically one way to think about it is you're putting out a pretty good baseline strategy. And, there's future work that can think about sort of more complexities, but, you want to be thinking about the layer one pricing, and you want to decide essentially at a high level to post when it's cheap to post, but you're also highlighting that it makes sense to essentially post in batches, like a threshold strategy is what you find. But I want to, with the time we left, I want to sort of pivot to the other part of the paper, because we've been talking a lot about fees, but we've been talking about L1 fees, right? And of course, there's an important decision variable that the rollup itself controls, which is setting the fees on the rollup, and you all study this too. And so, could you maybe, Ciamac, if you could come back and tell us about what are the considerations for the rollup operator to begin with in terms of setting fees? And then maybe help us think a little bit about, what the right way to think about that is. And then we can get into your results about this too.
Yeah, sure. So I think one thing that's sort of novel about this paper is I think this is sort of the first paper which jointly considers these two issues of how to post data to the L1 and how to set fees on the L2. And as I'm about to explain, they're actually very tightly linked. So when a rollup operator is figuring out how much to charge, they're thinking about two things. So first thing they're thinking about is when a user posts a transaction, later on they're going to have to post it to the L1. So one thing that's important is the L1 costs. Right? How much is it going to cost for me to sort of take care of data availability and sort of whatever, right? But there's a second component in that the L2 has its own operations. For example, if you submit a transaction to the L2, it costs the L2 operator money to sort of execute that transaction and process it and so on. And maybe even more importantly, the L2 also has a limited amount of blob space, right? It may be higher throughput, it may be a faster chain with greater capacity, but that capacity still has to be allocated and priced. So that leads to sort of two main considerations. The first consideration is to be able to pay the L1 costs. And the second consideration is to make sure you're covering your L2 costs, but also more specifically, make sure you're managing congestion on your L2, right? If the L2 is receiving too many transactions from users, maybe increase the fee. If it's receiving too few, maybe decrease the fee, and so on. And so what we propose is essentially on both of these sort of considerations, developing a separate fee. So one fee which is meant to capture L1 costs, one fee which is meant to capture L2 congestion. Both of these are updated in a dynamic EIP 1559 kind of style. So for example, the L1 focused fee, if I'm raising more money than I need to pay on the L1, I'm going to decrease it. If I'm raising less money and my L1 costs are higher than the amount of money I've been getting, I need to increase it, right? Similarly, for the L2 congestion, the index is not going to be, how much is it costing me on the L1? The index is going to be how big is the L2 blocks versus, let's say, my target level. And again, just like EIP 5059, increasing prices if it's too high and decreasing prices if it's too low. So we have these two sort of separate fees, and what we propose is actually to charge the greater of the two, right? Because it's kind of like an and, right? You want to be budget balanced on your L1 costs, and you want to manage your congestion on your L2. And so you don't necessarily need to charge separate fees for both of those two, because maybe if I happen to charge a very large fee to cover my L1 cost, my L2 congestion will be low automatically. I don't need to charge on top of that, right? But what you do need to do is you need to charge the larger of these two fees, and that's the kind of fee structure that we propose.
I see. Davide, do you want to add anything to that? Okay.
Yeah, I think beautifully painted the picture of how the mechanism works. Yeah.
Okay, awesome. So now you mentioned sort of the updating rule as sort of akin to the updating rule in EIP 1559, the base fee updating rule over there, right? Which essentially is looking at the past and sort of using a weighted average scheme to update. I actually haven't looked into the work on this myself, so I'm kind of curious about like how effective that is empirically, in the sense that I think initially a lot of people looked at it and went like, the intuition, and here I'm talking just about EIP 1559. I was like, okay, the intuition seems to make a lot of sense, but I wonder whether it's going to work in practice. I mean, because essentially part of what's happening here is like you're kind of forecasting demand forward, right? And you're using the recent past to do it in this kind of rolling average way. I don't know, Maria, maybe could you provide a bit of context on sort of how that's gone for EIP 1559 as a way to get a sense of sort of how this might work for this particular case?
Sure. So I think there's two different points here. So the first one is how it works for the L1 managing congestion, and so far it's been fairly successful. So if you look at the data, you see that most of the block utilization is around the target. So you see these cases where when there's some spike, it actually very quickly the block utilization, like after one or two blocks, it actually comes to the target. So in that sense, it has been fairly successful. But I think for the specific question of how it works for the L2 setting fees, this is actually a question that I think it's a bit more nuanced, and it's something that I think could be some interesting analysis for the researchers hearing us, which is, in a way, rollups are trying to forecast what will be the costs in the future, right? If you are a rollup that is posting every block, then this is fairly easy. You just are looking one block ahead, so it's fairly easy to forecast. But if you are maybe a smaller rollup and you need to wait a few blocks, this now turns into a more complicated analysis. So you actually have to do some forecasting models that will look at maybe utilization from other rollups and past data, and you actually build a forecasting model. So in those cases where you are actually charging fees now, but you are only having your costs 4 and 5 blocks down the line, it's actually a question in my mind is like how effective just using a 1559 mechanism works in practice. So it's something I don't know, and maybe it's an interesting research question for the audience.
Maybe I can give a tip here. So in our previous paper with Ciamac, the one called Optimal Dynamic Fees for Blockchain Resources, where we look at essentially resource pricing on the layer 1, we actually have these analysis. So because basically in that paper, we look at, okay, take the current 1559 rule on the layer 1, and then let's try to come up with a control-based optimal dynamic policy that it's actually more principled. It's not like very advanced, but it's like a proper optimal controller, where like essentially at each step you try to estimate what the demand state is, and then the update rule is a bit more principle based on the elasticity of demand also that you estimate. And we find that this is much better than the current 1550. So basically 1559 is quite slow in responding to like market changes. And I remember like we were looking at this metric, what is the bias of the realized amount of gas from the target, and what is the variance of the realized amount of gas. And in both of them, if you do the optimal dynamic policy, you have like quite a substantial improvement. But one reason in this work we decided to like stick to the simpler like 1559 style policy is because like maybe like connecting back to the title of this podcast is like from research to mainnet. Like in blockchains, those like more complicated policies, and as Maria was saying, you could even think about like more advanced forecasting, like using like neural networks for that. But they are quite difficult to implement, and you also want simplicity of these protocols. So we felt that this was not maybe like the main point of the L2 framework paper. So we want to stick to something simple that maybe can be also like implemented like straightforward by some L2s that want to experiment.
Yeah, wonderful. Thanks for sort of pointing out, the name of the podcast, that is, from Whiteboard to Mainnet. And I think on that note, Maria, when we have you on the call, would you like to maybe provide some context and shed some light on the future scaling roadmap of Ethereum, both at the L1 level as well as blobs, maybe?
Sure. So the current fork that we are working on is the Fosaka fork. So it's scheduled to mainnet later this year. And a key change, as Davide has alluded to, is peer DAS. So this is a big change to how blobs are handled in the Ethereum network. So as I was saying before, like there's two reasons why data is expensive in Ethereum. The first one is the in-the-moment burst. Like you have to essentially make sure that all the validators have the data so they can attest that the block is valid. So this is cost number one. Cost number two is the after the fact, this data needs to be stored by nodes indefinitely. And with the block market, we actually solved cost number two, because now this data is ephemeral, so it doesn't need to be stored forever, and so they can be cheaper. But there's still cost number one, like the in-the-moment cost of propagating all this data. And this is what peer DAS solves for. So now instead of all validators having to download all the data, they just download a sample of the data. And with that sample, they can validate together that the entire data was made available. So they are kind of sharing the work of validating that the data was available. And so this actually unlocks further scaling, because now you don't have the limit on bandwidth, and you can increase the number of blobs that are actually being included in a single block. So this is scheduled again for Fosaka, which is later this year. There's another change there that is also relevant for scaling, or in this case for the L1 and L2 fees, which is so far the blob fees have been very, very low. And actually what is dominating the cost is not as much the blob fee, but actually the execution cost of that transaction, so the priority fee and the base fee. And so to fix this, there's EIP 7918, so having a bound on the blob fee that is actually the execution cost. So this will actually change a little bit the dynamics of the blob fees, and this is also scheduled for Fosaka. And what we'll do is it will actually have a lower bound effect on the blob fee. So it's essentially fees should be a bit more expensive after that. But with an additional scaling, we we can have also more room. So there will be some balancing effect there. Then for the next fork, which is Glamsterdam, so this is scheduled for middle of next year. We are already working on which proposals will be included in that fork. And there are two big changes. One of them, which will have some effect on the block market as well, is EPBS. So this EIP essentially will change how the slot is structured and will give more time for both transaction execution and blob propagation, data propagation. And so this will actually allows us also to scale. And another thing that Davide pointed out that is relevant is within these two forks, we will have additional changes, which are called PPO. So it's blob proposal updates. So it's essentially like these upgrades, they are just changing the parameter of how much blobs can be included in a block. So there will be a light fork. And so it allows us to, with PeerDAS, we introduce the change, but we keep the same limit. And then we monitor how the network is going and how PeerDAS is functioning. And as we see that the network is being able to handle more data, we slowly increase the number of blobs that blocks are carrying through these PPOs forks. So it's like lighter forks that only change this parameter. So these are the next two forks. So we hope that with this we'll have a lot of scaling both on DL2, but also there's a few changes on DL1, but I don't think they are as interesting for this discussion.
And I know we're almost at time here, but just to sort of like try and tie everything together, Davide and Ciamac, how do you foresee these changes to sort of like affect some of the insights that y'all have surfaced to the paper, or like some of your findings, if any?
Maybe one comment I would make is assuming that like the audience is like mainly researchers that are also interested in like making some impact on like some real world system like Ethereum, is essentially every time there is like a fork where like some economic mechanism changes, there is like some new opportunities to like study that market and like come up with like some new research question. Like I cannot anticipate like much changes versus like our current work, because as I said, it's kind of like a framework, right? But there is some interesting changes, like what Maria mentioned about like this EIP 7918. There is also a new EIP called 7999, like with 3 nines, which is about like unified fee market on the layer 1. So essentially, I would encourage people to like look at this upcoming changes and try to like drive inspiration for like research question, and maybe even join the discussion on the ETH research forum about these.
Great, awesome. Thanks for that. So I would just quickly like to conclude the podcast by saying a few closing remarks. Firstly, thank you so much for our 3 wonderful guests for joining us and providing us with a lot of insights for further deliberation and questioning. And we hope that everyone listening, had a great time. This podcast series is going to be more of a recurring one. We have, a couple more episodes sort of, lined up. But almost immediately, another one that's on our radar is in the 19th of September. That's happening 1 hour earlier than this one. So it's going to be 2 p.m. UTC to 3 p.m. UTC. And we're going to be joined by Urban German from UPenn, who has a lot of expertise on asset pricing and international finance and macroeconomics in general. And we're also going to be joined with Casper and Ansgar, researchers at the Ethereum Foundation, and they're going to be talking about proof of stake issuance and this sort of insights that we can get from academia along that topic. But that's all I have to say. And yeah, thank you everyone for showing up, and hope to see you in the next one as well.
Thank you.
Thank you.
Okay, yeah,
Right.
I think the stream is done. Yeah, perfect.